Yeah, go ahead.
Yeah, okay. Okay, thanks, Liu for the introduction, and yeah, thanks, Liu for organizing this wonderful Consensus Matter series. Yeah, I'm very happy to be the first speaker. Yeah, hope yeah the talk will be beneficial to the audience. So this talk is about quantum error correction and how to use conformal field theory to build a quantum error correction code. Um, so um, so in order to start, I think like probably you don't know many things about quantum error correction. So the first thing I will going to talk about is an introduction, very brief introduction to the error correction codes. And then I will go to more condensed matter side of the story, which is quantum critical systems and conformal field theories. And then I will just combine the two ingredients together to talk about the main topic of this talk, which is the coding properties of a conformal field theory. So far, it's mainly focused on the quantum information, but then if you really talk about physical system, you can actually understand these code properties using general notions of phase of matter, and especially generalization of traditional view of phase of matter into mixed states. I will briefly go into that, and then I will mention a summary and future directions of this work. Okay, let's start it. So the first story I want to tell is about error correction. So now we have quantum computer, but before we understand how quantum computer work, we first want to go through how classical computer actually works. So on the left-hand side is my favorite laptop. And as you know, all the laptop, whatever it is, it always boils down to zeros and ones. So if you have a disk on your hand, like all the data in the disk can be programmed into like strings of bit, which consists of 0 and 1s. But if you want to talk about storage, then there must be a chance to have some error, right? Like you put your disk on your hand, and then probably there are some probability that some of the 0 will flip into 1, some of the 1s will flip into zeros. That could totally be possible. You cannot just avoid it by imagination. So there must be some way to fix it. And that way is known as error correction code in classical computing. So, but things becomes a little bit more complicated in the quantum world because in the quantum computer, the 0 and 1s, they are not just 0 and 1s. Actually, you can have superposition between 0 and 1s. That is like Schrödinger's cat can be alive and dead at the same time. So you can have alpha 0 plus beta 1 as your information, where alpha beta is some complex number. So you can see there's a continuum set of information that you can store on a quantum computer, and that actually gives you quantum advantage. But then it also means that the source of error could be more complicated, right? Because now your alpha beta can be arbitrary complex numbers, or they can change in arbitrary ways. So for example, a bit flip just says that, okay, it's just a generalization of classical bit flip to quantum bit flip, where you change alpha 0 plus beta 1 to alpha 1 plus beta 0. But there could be also other types of error, for example, the phase flip. The phase flip just says that if you have a 0, you don't change the sign, and you have a 1, you put a minus sign in front of that. So remember that in a quantum system, this sign really matters because it actually has observable effect on interferometry. So this phase flip is really an error. So apart from bit flip and phase flip, you can also imagining like some type of like general unitary transformation on the state, which can be something that you don't control, so that would be an error. You have to fix like all kinds of error like this, which also forms a continuum set. So that appears to be much more complicated to correct. But the big idea of quantum error correction is that like you can use error correction codes just like classical error correction codes to correct quantum errors. So the idea of generically speaking error correction code is that you embed the logical information, that is that That is the information that you want to keep into a larger set of physical space. So for example, you could like store like 1 qubit into like 3 qubit, 1 bit into like 10 bits. And then if the physical space gets an error, it's still possible to retrieve the original logical information because you are just like embedding 1 bit into like 10 bits. So the 10 bits, even though some of them could have error, there's still a chance that you can still tell whether it is originally it is 0 or 1. So that's the that's the idea of error correction code. So far it might seem a little bit abstract, but soon I will give you one very intuitive example. Error correction code they can be characterized in many different ways, but the primary purpose is to be fault tolerant for computing purposes. So in order to characterize a good quantum error correction code, you need to specify how much logical information it can store and how much physical space you actually need, and how much error you can tolerate. So good error correction code must encode more logical information into smaller physical space while tolerating more errors. So that's apparently they have tensions to each other. But the goal of quantum error correction or error correction in general is to achieve this as much as possible. So a very much recent example that we all are familiar with right now is the 5G network. It's actually a classical error correction code which use the so-called classical LDPC code. So it can achieve the above like objectives in a very good way. And it has enabled us to transmit our data in a much faster way, as we can all experience. So that's the classical story of error correction. And then I will just tell you a very, very simple example of how error correction might work. So the simple example is called repetition code. So a code can be characterized by two numbers, which is n and k. So n is just the number of physical bits, and k is the number of logical bits. So here I have chosen to embed like one logical bit into three physical bits. So the encoding is given by you encode 0. If you want to store 0, you make 3 zeros. If you want to store 1, you make 3 ones. And then if one error happens, whatever bit it might be, like you can have 0, 0, 0 going to 1, 0, 0, or 0, 1, 0, or 0, 0, 1, or 1, 1, 1 go to 1, 1, 0, 1, 0, 1, 0, 1, 1. Then you can, and then the point is that you can still do a procedure called decoding procedure. This decoding procedure is to read off the original logical information. And the decoding is given by the so-called majority vote. So you just count. You just count whether the number of zeros is greater than the number of ones, or number of ones is greater than the number of zeros. Apparently, if just one error happens, then 0, 0, 0 still remains like more zeros than ones. So you can read off that the original information that is stored is 0. And if you find more ones than 0, then you know that the original information is 1. But this procedure will fail if there are more than one errors, right? So if you have 2 errors, you will wrongly identify the original zeros to ones. So that is the drawback of this code, which it can at most crack 1 error. But there's a simple generalization of this code, right? Like you can try to store like 1 bit into n bit. You just make n copies of the original bit. And in this case, you can tolerate more errors, and by this maximal, by this majority vote decoder, right? So as long as less than half of the bits get flipped, you can always achieve the decoding correctly. So at most, you can tolerate n-1 over 2 errors. Yeah, so that's the repetition code, which is a classical example of error correction. And then we will see how this can be generalized into our quantum world, or cannot be generalized into our quantum world. So the first obstacle coming from the non-cloning theorem. Non-cloning theorem says that quantum information cannot be copied. So if you want to like encode this logical information alpha 0 plus beta 1, that is the quantum bit, into a larger set of Hilbert space, what you cannot do is you cannot just prepare 3 three identical copy of it. Because like this operation is not a unitary operation, which is not allowed by the long cloning theorem. Okay, so instead, for the quantum repetition code, what we can allow to do is we embed 0 into 0, 0, 0 and 1 into 1, 1, 1. Like we don't like clone general state, but we just clone like particular 0 state or 1 state. That is so that is possible by a unitary operation. So you can see that alpha 0 plus beta 1 is encoded into alpha 0, 0, 0 plus beta 1, 1, 1. But then you see that there's a very sharp distinction between a classical case and quantum case. That is, in quantum case, if you do this encoding, then the state that you have must have some entanglement. So you see that this alpha 0, 0, 0 and beta 1, 1, 1, they are superposed to each other. So each of the qubits, like any of the two qubits, like they are so these three qubits, they are entangled with each other. So you actually need quantum entanglement to prepare this code. So that is a distinct feature from the classical world, which you can make error correction possible. And we will soon see that in our case of like a conformal field theory, entanglement also plays a huge role in error correction. And now let us also consider error happens. Like you can consider a big flip error, for example. So then there are three possibilities that either you flip the first spin, or you flip the second spin, or flip the third spin. Oh, sorry, in the first line, I think there's a typo. It should be alpha 100 plus beta 011. Yeah. So yeah. So now you have three possibilities of having one bit flip. But then how do you want to decode? So you still want to use the majority vote decoder, right? So you want to count whether there are more zeros than ones or more ones than zeros. But you should be careful also here that measurement can destroy quantum entanglement. If you just measure like sigma z of the first qubit, you will basically destroy the entanglement because you already measured whether Schrödinger's cat is dead or alive. Then it is either dead or alive, and you cannot change it. So so then one have to be careful about decoding. And the axioms of quantum mechanics tells us that only eigenstate of the measurement operator do not change. So that helps us devise the decoder. So the decoder goes as this way. So you'd measure Z1 times Z2, Z2 times Z3, and Z3 times Z1. Like you don't measure like Z1, Z2, Z3 independently, but you measure the product of two of them. And in fact, as you can check on the right-hand side, every state is indeed an eigenstate of these three operators. So measuring these three operators won't change the state. So in fact, by measuring these three operators, you can get three of the outcome. Either you get -1, 1, -1, or -1, -1, 1, or 1, -1, -1. And in these three cases, you know which spin gets flipped, right? And in the first, for example, in the first case, you know that the first spin is flipped. Then you would like to apply sigma x1 to the first qubit to reverse this error. And then if you get the second syndrome result, you get the second measurement result, then you would apply the x2, and if you get the third measurement result, you apply x3. If you get like all the z1, z2, z3, all the three operators to be +1, then you say there's no error, so you don't apply anything. So that is the analog of majority vote decoder in our quantum world. So far we have already like construct the quantum repetition code, which can like embed like one qubit into three qubits, and we have shown that like this code can tolerate one bit flip error, and in fact this can be generalized to n qubit as in the classical case, and can correct n-1/2 bit flip errors. Okay, so now we have construct a quantum error correction code, and we show it can tolerate some kind of errors, but it is good. Actually, it's not, because if you consider phase flip error, then a phase flip error will actually kill the logical information to see what to like you cannot correct a phase flip error. So to say why, if you consider a logical state that is alpha 00 plus beta 111, and you make a phase flip error on the first qubit. So remember, in a phase flip error, you change a sign in front of ones, so it changed to alpha 00 minus beta 111. But this state is exactly the same state as a different logical state, right? Like if you start with like alpha 0 minus beta 1 instead as your logical state, then you would get the same state, even without an error. So since the state is the same, so there's no possible measurement that can distinguish one bit flip error with no error, because like the state becomes the same after you have one bit flip error and after no error, but with another logical information. So thus we can conclude that bit flip error is not correctable for quantum repetition code. So this code is not so great because it cannot tolerate phase flip error. Sorry. Yeah, there's a typo here. So phase flip error is not correctable for quantum repetition code. Okay, so now I have given you an example, so there are many quantum error correction codes which I cannot enumerate, and in fact, the work that started here, which is using conformal field theory as an error correction code, might not be the best error correction code that we could ever have, but still, there are some really good quantum error correction code which can actually tolerate a lot of errors, arbitrary type of errors. So, so in order to actually discuss that, we have to first go into a little bit deeper into the formalism of generic quantum error correction. So a quantum error correction code is first given by the so-called encoding procedure that we just have. So encoding procedure is going to embed like logical information into a large set of physical Hilbert space. So this is given by the encoding channel. So remember that in the quantum world, the only operations that you are allowed to do is a quantum channel. And by quantum channel, what we mean is simply unitary operations plus tracing out some qubits. So that's the only allowed quantum operation that you could have. So the encoding channel must also be a quantum channel. And then we want to ask whether there exists some decoding channel that could reverse the noise. And we will use N to denote the noise model, which is also a quantum channel. So the decoding procedure is such that when you compose the encoding with noise and with decoding, then the composition of these three maps must be close to the identity map. So that is that is you can retrieve the original logical information. So there are like two classes of quantum error correction codes, where the first one is called perfect exact code or perfectly correctable errors, and that is given by the exact equality equal to identity. But there are also approximately correctable errors, and where CFT code is in one of these examples, where you can at most achieve this approximate sign, not exact sign.
Question.
Yeah. Mm-hmm.
So, like when you say approximate, right? Like which norm should I be thinking of?
Sorry, what's the question?
When you say approximate, which norm should I be thinking of?
Oh, norm. Yeah, that's great. Yeah. So there's one notion called channel distance, and the channel distance is basically the maximum Bose distance between between the inputs like between like two output states, where you can input like whatever input state into the left hand side and the right hand side, and then you run the channel and you get two different output states, right? And you just measure the Bose distance and you maximize over this Bose distance. That's yeah.
So
that's
is that the diamond norm?
No, yeah, I'm not sure. Yeah, I have to search for it, but yeah, but I will also tell like I will also there are many, there are many different norms. but they are kind of all equivalent because they are all upper bound and lower bound by each other.
No, they are. But I mean, operationally, the diamond norm has a operational meaning, right? Like in terms of optimal distinguishability
Uh, yes.
in
So
channel input and output. So
yeah,
like what eventually when you talk about your approximate error correction in CFT, which one should I be thinking of? Like which norm are you using? Just
I'm actually using the so-called channel distance. I'm actually I'm sure it's not the same as I'm sure it's not the same as diamond norm, but
okay.
uh, it should be kind of equivalent.
Okay, thanks.
Yeah. So now when we talk about like exact code versus approximate code, actually approximate code, even though like you cannot reverse the error exactly, but they may have better performance in the case that you can use a smaller physical table space or you can tolerate more errors. And that is given by this, like some examples are given by these classic examples. But conformal field theory also fall into this class. That is what I will talk about today. So, okay, and since this is a condensed matter similar, I think I'm supposed to talk some some condensed matter. So why condensed matter physicists should be interested in quantum error correction? So as I just tell you that essential to quantum error correction code is quantum entanglement, right? Like in order to do some encoding, you must have quantum entanglement between your physical qubits. But entanglement also plays an important role in quantum phase of matter. If you think about like superconductivity, superfluid, like the ground state, they are highly entangled. So entanglement also characterize like this non-trivial quantum phase of matter. So one fruitful example of like combining quantum phase of matter and quantum error correction is called surface code, which is put forward by this gentleman, Dennis Freskill, 20 years ago. And alongside with the surface code, there's a notion called topological order in condensed matter systems. In fact, you can show that if you have topological order, that is a good error correction code. And if you have, so that is a good connection between condensed matter physics and quantum error correction. So, and so can we generalize this perspective like to more complicated models? Like um, apart from topological code, can we use other phase of matter to store quantum information? Yeah, and the answer is yes, and it's actually extensively studied in the past literature. Not very extensively, but there are many examples explored. And for example, ferromagnetic Heisenberg model has been studied, and also like holography, if you know about that. It's a theory of quantum gravity. It's also quantum error correction code in disguise. So and so it's important, like the study of like quantum phase of matter can really help you build some quantum error correction codes, and also the studying of the coding properties also shed light on the information theoretic perspective of this phase of matter. So that is the perspective that we will take, and we will take this perspective to study quantum critical systems. Okay, so now I will go into quantum critical systems and make a brief introduction on conformal field theory. So in general, if we talk about condensed matter models, we want to start with local Hamiltonian, right? So we put a lattice. We have a lattice which can represent actual atoms in your lab. And then you have some electrons moving around, which can hop to each other, and that gives you a local Hamiltonian. A local Hamiltonian can be very complicated, but if you want to classify it, you can broadly classify them into the so-called gapped phase and gapless phase. and they are distinguished by the low energy spectrum of this Hamiltonian. So you just diagonalize the Hamiltonian and you get the low energy spectrum from low to high. And for gap system, you could have very, very close degenerate states, and then there's a finite gap delta, where you reach the next energy level. And then there's another class called gapless systems, which has infinitely many low energy eigenstates as you make the system size larger and larger. So all the low energies actually collapse into the same energy as you make the system size larger and larger. So in that case, you would have like the infinite number of low energy degree of freedom, and that typically makes your system more complicated. So for gap system, you could have trivial insulator and also topological order, but for gapless systems, you can describe like conductor like a metal and also quantum critical points, which I'm going to talk about today. So to give you one very simple example, and actually this is the example that I will treat today. This is the Ising model. So you have this sigma x interaction between two nearest neighbor qubits, and then you have a transverse field that sigma z, which has a coefficient g in front of it. And if you tune g from 0 to infinity, you will observe some quantum critical behavior in the ground state of this Hamiltonian. So to see that, you just first tune g to infinity, and if you tune g to infinity, you see that the Hamiltonian only have one term, which is like sigma z on every side. So now the ground state must be a trivial state, which is product state against all the system sides. So which is 0 to the power of L, and that gives you from a quantum error correction perspective that cannot store any non-trivial logical information. So I call it a trivial code. On the other hand side, if you have g equal to 0, then you could have like you have a degenerate ground state subspace, which is given by alpha times plus to the L plus beta to the minus to the L, because like this x operator only demands all the spin to be pointing in the same direction in the x basis. So there could be two possibilities: either they are pointing to plus or they're pointing to minus. But this is a quantum system, so you could have any superposition of this as an eigenstate. So as I have just tell you that this code subspace is actually identical to the repetition code, right? Because in the repetition code, you also repeat the same state for n times. So we know that on g equal to 0, there are a degenerate subspace, and this degenerate subspace can be described by a repetition code. So then we know that in the middle, there must be a phase transition, because you want to transit from two different ground state, or like a degenerate subspace, to a one trivial ground state. So in the middle, there must be something dramatic happens, and that one is given by the g equal to 1, which is the quantum critical point. And that is also known as a CFT. And in this talk, I will study like the coding properties, like how much logical information can you store in this code. Okay, so one important properties that distinguish this critical point from like the gap phase from on the left and on the right is that the ground state is long range correlated. So if you look at the 2-point correlation functions on the ground state of the critical system, then you will get a polynomial decay instead of exponential decay. And there's a power, very important power called scaling dimension, that characterizes how much the power law is. So for example, for the Ising model, you can actually exactly solve that the correlation function between xx decay as like the distance to the -1/4, and yy decays as distance 9 over minus 9 over 4, and zz decay as distance to the -2. And actually, these numbers will be very, very important in later on of my talk. So yeah, please remember these numbers, and we will go on. So why conformal field theory are important? Actually, so if you talk about quantum phase of matter, there are many, many kind of phase transitions. And usually this type of, usually a phase transition, they are described by conformal field theory in the thermodynamic limit. So in other words, if you know RG flow, then it means that the lattice model actually flows into a conformal field theory. And that means that different microscopic models may be described by the same CFT in the sense that they might have the same scaling dimensions. So in many cases, like the CFT itself is only determined by the dimensionality of the system and the symmetry of the system. So in the Ising model, if you ensure there is a Z2 symmetry, basically you will always get the Ising model. The Ising universality class in the continuum limit. So Ising model is just one way to realize such a phase transition, and there are infinitely many ways to realize the same phase transition. So that universality gives conformal field theory like a very important role in phase transitions. And CFTs, if you want to characterize the CFTs, then you would need something called conformal data. And this conformal data completely specifies all the correlation functions. And in many cases, this data, they are discrete. And and I will not go into the full like theory of conformal field theory here, but I will mention. Yeah, go ahead. Oh, okay, no question.
Actually, I do have a question. So about this 2-point correlation function. So you're taking this expectation of this OI dagger OJ. So which state like you're taking this correlation with respect to?
Yeah, good. Yeah, it's a ground state. It's the ground state. So we always look at the ground state. So okay. Yeah.
Thanks.
Yeah. Okay.
Wait, I also have a question. So for the correlation function of the Ising critical point, the Y has scaling dimension 9, 8.
Yes.
Oh, so this has been numerically confirmed. I didn't know that before.
Yeah. So it's a descendant of X. Yeah.
That's a coincidence of this particular model, right?
That's actually related to the time reversal symmetry. So actually, why like if you look at the complex conjugation, then the model edge is invariant on the complex conjugation, but Y would change sign on the complex conjugation, and that makes you that Y cannot be distinguished. Y cannot be identified with the spin operator, because spin operator is a real field, so it can only be identified as the time derivative of spin field.
I see. Thank you.
Okay. Yeah. Okay. So now I just briefly introduced you into conformal field theory. Sorry for not so enumerating, but the Ising model is the one example that we will talk about. Okay. And then I will go into like the coding properties of the CFT, which is the main result of this work. So if you want to take a quantum Hamiltonian and you say, okay, I want to regard this as a quantum error correction code, what can I do? Okay, in fact, it's you just need to look at the energy eigenstate. So you first diagonalize the low energy eigenstate, and you could find, like, for example, gapped or gapless. These are just two classes that your Hamiltonian must fall into. In the gapped case, you would like to choose your code word to be or the physical Hilbert space. The logical subspace to be the low energy part of this of the spectrum. So, for example, for the repetition code, you just take your Hamiltonian as xi plus 1, and then the ground space subspace is just given by a 2-dimensional subspace, which is the repetition code. So, so for the gap case, you just choose the lowest energies. There's no ambiguities. But for gapless systems, there's a little bit ambiguity, because there are many eigenstates that will collapse into the same energy in the thermodynamic limit. But what you can do is just you can choose like a number d, which you determine as the dimension of closed subspace, and you just put you just encode like 0 into the ground state, 1 into the first excited state, and 2 into the second excited state, 3 into the third excited state, and so on. You do this for at most d times where d is predetermined, and then that would give you like an encoding. And the goal of this work is to see like what kind of error can this encoding tolerate. And in order to talk about errors, we also choose some type of error models. And in this work, we will choose a local independent noise model, which is common like in a realistic world, that is saying that each of your physical qubit has some probability, has the same probability to suffer from an error, and that is described by this tensor product structure in the noise model. So so as I have mentioned in the introduction, like in the past, like this type of paradigms have been studied before in the context of a Heisenberg model or ETH systems. And the lesson that we have learned from previous studies is that code properties are closely related to physical properties of the phase. Like the toric code is closely related to the topological order, and ETH code, as the name suggests, is closely related to the chaotic properties of the Hamiltonian. Yeah. So in this work, we will see how like CFT, the interplay between like the interplay between physics and quantum error correction is fulfilled in the CFT case. Okay.
So here, do we assume each channel is acting on one side?
Yes.
If in reality, the noise may act on multiple sides, will this change the story?
Yeah, it will change many aspects of the story, but it will not change qualitatively the story. So for the torical, if you look at torical, then correlated error, they are much harder to decode than other type of error than independent errors. But if you talk about like the CFT code that we have today, then you can think of RG, right? You can think of renormalization group, which could combine like many of the qubits into one qubit. Then multi-site error is kind of equivalent also to local errors. So there's no much qualitative difference.
But I think even in the picture of RG, I may think the multiple site errors will be equivalent to nearest neighbor errors, not just a single set error.
Yeah, I think you're right. Yeah, but yeah, that will not that will not change the story that I will tell. It will of course change the decoder very much, but it won't change whether the error has a finite threshold or not. It will change the threshold, but it will not change whether the threshold is equal to 0 or not equal to 0. So yeah, the statement that I will make is not very sensitive to the locality, as long as it is quasi-local.
Okay, thank you.
Hey, so I have another question. So do we just take like all the eigenvectors of the energy eigenstates as the as the code space? I mean, like what's spanning the code space? Is that like what's being proposed here? Or?
Yes. Like you don't use all the energies, but use the lowest energies. Like for the gap case, you just choose like the energy eigenstate below the gap. How many degenerate eigenstates you have, you choose that as your code substrate. But for the gapless one, you just choose the first several eigenstates that you
right. So in this definition, so you have like this H code spanned by this phi alpha, and you have like D states here. So
yes.
these states are the states that are below this gap. Is that correct?
Yeah, for the gap case, yes. But for the gapless case, like there's no gap, so you can choose whatever D you like.
Okay, I see. All right, thanks.
Yeah. Okay, that already gives us the first hint on why CFT code may be better, because you can encode more information. I will go a little bit into that later in the talk. Okay, so
I have a related question. I guess for this to work, we have to identify the Lorentz states that are adequately described by a CFT.
Yes.
If we start from a lattice system, maybe the known distance physics is described by the CFT, but if we look at the high energy states, they are not described by the CFT, then what's the criteria for us to check whether this state can be viewed as a CFT state?
Well, yeah, that's a good question. First, I can assure you that for whatever d equal to order 1 number, like you give me d equal to 1000, there must always be a system size such that when you exceed such system size, all the like d eigenstates they can be treated as CFT states, right? You agree that when system size go to larger and larger, then the low energy state should be more and more like the CFT state. But we also know that the CFT spectrum is also infinite. So whenever you fix a finite cutoff, then you would always get a CFT-like state in the thermodynamic limit. And then regarding the criteria, I think we can look at the energy, for example, whether the energy is close to the formula that the Cardi formula that I read here. You can also look at the matrix element to see if they agree with the OPE. So yeah, all of these can be treated in a systematic way. But when the system size goes larger and larger, I can always assure you that the low energy eigenstate must be described by CFT.
Okay, thank you.
Good. Yeah. Okay. So this is the example of the Ising model. So if you look at the low energy eigenstates, yeah, there are many, and then the energy is given by this formula, which is like 2 pi over the system size times something called scaling dimension minus a constant. Okay, you don't have to care about the constant. But this delta is exactly the scaling dimension that we just talked about. So the theory of CFT tells us that low energy state, they are organized into so-called conformal towers, and you can already see that energy eigenstates have a tower structure, right? So each of these towers, they are labeled by a different color. So in the case of Ising model, you have three of them, and each tower is actually infinite. It's infinitely go up. So you can, if you want to only keep finite number of them, that's completely fine. But any finite number of them will fall into either of the conformal tower. So a key property of the conformal tower is that the scaling dimension differ by integers. So if you look at all the like green dots, they always fall into scaling dimension equal to integer, because the primary state, which is the lowest one, has scaling dimension equal to 1. So then any state that originates from this state always have scaling dimension integer. So here, in order to choose a closed subspace, we can just choose arbitrary number of low energy eigenstates. For example, you can cut off at scaling dimension equal to 7, and I believe there are kind of 100 state in the figure. So now the closed subspace is kind of 100. Dimension is 100. So you choose arbitrary number of them, and that gives you the encoding. Okay. So so then we want to talk about whether this code can tolerate errors. So remember that for repetition code, we can only correct bit flip errors up to 1/2 of the total system, right? So so here for CFT code, actually things are a little bit complicated, because first the code become approximate. So for repetition code, the code is exact. If you look at like errors that is like 1 or 2 errors, right? If you just have 1 error, this error can always be detected and can always be perfectly corrected by the majority vote decoder, right? But for CFT code, actually you lose that property. Instead, you would have an approximately correctable error, and in fact, as our very well known colleague Neil Laplane shows that like this condition, Neil Laplane condition, is the condition for exact decodability. So now phi alpha and phi beta, they are the code word. Like they are they are the logical state that you encode, and then EI and EJ, they are just errors. Like whatever errors you could have, you can, for example, put a poly Z error on one side and put poly X error in another side. Yeah, that's good enough. And exact decodability requires that this matrix element of this thing must be diagonal with respect to the alpha beta index. What this means is very simple. It's just error cannot destroy distinguishability between code word state. Suppose like you start with phi beta, right, which is a code word, and then there's some error happens. You still want the state to be distinguishable from another state, phi alpha, which is contaminated by the error EI. If these two states, they are not distinguished by each other, then of course there's no way to distinguish phi alpha and phi beta after the noise, and there's no way to retrieve the logical information, right? So this is the condition for exact decodability. But if you look at CFTs, then for CFTs, actually just one error will already violate this condition. Like you take this EI to be identity, which is no error, and you take EJ to be some operator on the I side, let's say. So that gives you an OI, and that represents the error operator. And then if you look at this metric element, in general, for CFTs, there's something called OP coefficient, and then there's a system size to the power of scaling dimension. And again, you see that scaling dimension is very important here. And as you can see, L, if you want L to be larger, if you want L to be finite, let's say L to be finite, then this number is always non-zero, given that C is not equal to 0, okay? Like this number is non-zero, and that already violates the neo-Laflamme condition for exact decodability, and that means that CFT code can only be an approximate code. But this approximation can be controlled by increasing the system size. When you make the system size larger and larger, you will see that the neo-Laflamme condition, at least by this local error, becomes closer and closer satisfied. And because C is just one number, it's some number, so it doesn't scale with system size. So as long as you take L goes to infinity, this number always goes to 0. So so CFT code is approximate code against local errors. The conclusion we make is that as L goes to infinity, any local errors can be correctable. And if you make L larger, then the error is more correctable. If you make L smaller, the error they are less correctable. But any error supported on O1 number of qubits can be corrected when you take L goes to infinity first. So that is already some very distinct features from the repetition code. Remember that for the repetition code, if you have a single phase flip error, you will destroy the code immediately, right? But for the CFT code, the single bit flip error or phase flip error or a single any error cannot really destroy the code as long as you first take the thermodynamic limit. Or even you just take L to be very large, still like the code is approximately correctable. It's not like the repetition code that it completely destroyed the state. Okay, so that is one feature of CFT code.
Excuse me, I have a question.
Okay.
Yeah, so we know that in conformal field theories, for some 3-point functions that are not invariant under the conformal transformation, we know that the correlation function of the 3-point function is automatically 0. Can we use this fact to build error code? I mean, here you said that in the second equation, that were on the left-hand side of the second equation, which is literally a 3-point function, you have a non-zero result. And we know that for some 3-point functions that are not invariant in the conformal transformation are automatically 0.
Yes. In fact, I think generically speaking, that case requires some symmetries, right? Like yeah.
Yes.
Yeah.
So can we use this 0 to build error correction code and make the error correction code exact, not only approximate?
Okay, you can still make like 1 point, like one error exact. I'm pretty sure by your construction you can make one error that can be exact correctable. But when you consider 2 errors, let's say you could have OI on one side and you have OJ on another side, then the symmetry will typically doesn't stop you from giving a non-zero number. So for 2 errors, still be approximate.
Ah, I see. In that case, you have a 4-point function. I see.
Yeah. Good. Okay, great. So Okay, probably yeah, I will skip this detail, but okay. This is also a very important aspect of like quantum error correction, which tells you whether an error can be corrected or not. Like remember that like before we have just for the repetition code we have like constructed a decoder, but for many cases, we just want to know whether the error can be corrected. Like we just, of course, like constructing the decoder is important, but we first want to know whether in principle there exists a decoder or not. And that is given by the so-called like decoupling condition that is very widely used in the quantum gravity community. But it's actually first put forward in quantum information community. So so here I want to introduce the state that is psi QR, which is the maximal entangled state between a reference system and a quantum system, which is the physical system of your code subspace. So phi alpha is just a code word in your physical system, and alpha is just some auxiliary space where you call it a reference, and you first create a maximal entangled state. And then you want it to go through a channel. You want the quantum system to go through some noise channel. And we know that a noise channel must be written as some unitary transformation between the quantum system and some environment. So you have some environment that is initialized into 0, and you use this unitary transformation to couple the system with the environment. And then you trace out the environment, and that gives you the noise channel. And if you trace out the quantum system instead, rather than tracing out the environment, that gives you a complementary channel. That's just some name. But then the decoupling condition basically says that if you apply the complementary channel, then you require that rho ER is a decoupled state between environment and the reference. That basically means that quantum information doesn't leak into the environment because you are tracing out the environment. You don't keep the environment, so you don't want any information to flow back to the environment. So that is basically what this decoupling condition is saying. Like if the decoupling theory condition is satisfied, then there must exist some decoder which achieves this fidelity, entanglement fidelity Fe equal to 1. So also just to answer one-way question, like what's the way to characterizing approximate error correction? Like this entanglement fidelity is one way to characterize how good approximate quantum error correction is. Okay, so exact error correction means Fe equal to 1, and that is equivalent to decoupling condition. And actually, this can be readily just generalized into approximate case, where you just compute the mutual information between the system, between the reference and the environment. If the mutual information is 0, that will mean that reference and the environment are decoupled, and that means perfect error correction. But if the mutual information is small, that also means that if the information can be partially or kind of exactly like recovered, which is given by this inequality, that the entanglement fidelity must be greater than 1 minus 2 times square root of delta IC. And so if delta IC is which is the mutual information between reference and environment is small, that means that the information can still be approximately corrected. And there's also a better bound given by channel distance, which I'm not going into detail. And when we are interested into like this reference, like, yeah, so this contains like other type of characterization of approximate error correction. Okay, so so now let me summarize what we have just gone so far. So we have for the CFT code, we have the encoding, which gives you the CFT low energy eigenstate that can be achieved by a mirror or a variational quantum circuit if you want. But that part is not important as long as we have prepared the code word, the encoding part is done. And then we just want to apply a noise model, which is everywhere independent noise, which is given by this defacing noise. Like this defacing noise is simply says that at each site j, there's a probability 1/2 of the p where the state is not changed, and there's a probability 1/2 of the p where you flip the spin on the direction of sigma alpha. Well, alpha can be either x or y or z, right? You flip the spin on the x direction or the y or the z direction. So that is our noise model. And the coherent information story will give you whether the error is correctable or not. If the error is correctable, then it means that the coherent information remains unchanged as you take the thermodynamic limit, and that means like the error, like the coherent information doesn't change. That just means that the error is correctable. And if instead the coherent information drops, then the error is uncorrectable. So that is the correctability condition for the CFT code. So that gives me into my main result, which probably, yeah, I'm going a little bit over time. So yeah, I will be just spend the last few minutes on this main result. So the main result is that for a CFT code, there's a finite decoding threshold for the dephasing noise that I mentioned above, if and only if the fusion algebra generated by the jump operator has the minimal scaling dimension bigger than 1/2. It's a little bit complicated. If you disregard the fusion algebra part, it just means that the scaling dimension of the sigma alpha operator, the sigma alpha could be sigma x, sigma y, or sigma z operator is bigger than 1/2. Okay, and for the Ising CFT, you have x scaling dimension 1s, y to be 9s, and z equal to 1, and you see that y and z satisfy this condition, and x does not satisfy the condition. So the conclusion is that x error does not have a finite threshold, and y and z error have a finite threshold. And what if you want a CFT that has like all the operators to have a finite threshold? And actually there exists such a CFT, but this CFT, they are not very easy as the Ising model. That requires all the scaling dimension to be greater than 1/2. That includes, for example, the so-called monster CFT, or the Wills-Dumino-Witten model with FUN symmetry, but you need n greater or equal to 3. Yeah, that's kind of interesting that you cannot really realize it using spins, but you have to use qubit. Okay, so that's our main result. So
excuse me.
Yeah.
Sorry, could you please explain what is the jump operator?
Oh, sorry. Yeah, the jump operator simply is the sigma alpha here. Yeah, the sigma alpha, the direction of your bit flip. Yes. So.
I see. Thanks.
Yeah. So here you could either flip your spin in the x direction or the y direction in the z direction. And I'm claiming that if you are flipping them into the y and z direction, then it has a finite threshold. That means you can correct these errors up to some probability of errors. And then, but on the other hand side, if you have x errors, you cannot correct them by a finite threshold. You can still correct all the one number of them, as I have shown you before, but you cannot correct everywhere noise with a finite threshold.
So if a lattice system, the microscopic degrees of freedom of the lattice system is qubit. If this is the case, then we always have 3 jump operators. Is it correct?
Actually, yeah, you either have the 3 jump operator or a linear combination between them. You can have x plus y if you want.
I see. So this jump operator, the property of the jump operators depends on the microscope detail of the CFT, not only the universal data of the CFT. Is it correct?
Yes.
I see. Thanks.
Yes. So there's an interplay between like microscopic model and and the CFT. You first need to identify each of the microscopic operator with CFT operator in order to make this statement.
Yeah, I see. Thanks.
Yeah.
Hello, I have a question.
Mm-hmm.
I maybe I'm not understanding everything yet, but I guess that the half comes from some scaling dimension argument that threshold delta larger than a half. Is that right? And if I'm talking about a irrelevant, or a delta that is violating that condition, what would be the value for the threshold?
If you violate this condition, that means delta is smaller than 1/2. You only have 0 threshold.
Sorry. I misspoke. If you satisfy this condition, you said there's a threshold. So what is the value of that threshold?
Oh, okay. Yeah. So it depends on the models, but for the Ising model, the threshold is 1. Like it can correct maximal amount of error.
I see.
Yeah, depend on the model, but this result only tells you if you have a finite threshold or not.
I see. And
Unfortunately.
sometimes we do know that even irrelevant deformation to a CFT could wreak havoc if you give it enough strength. So does it mean in those cases, even if delta is smaller than 1/2, there could still be a finite threshold?
I mean, yeah, sorry, no. Delta smaller than 1/2 definitely means zero threshold, but delta bigger than 1/2 doesn't mean that the threshold persists to maximal threshold. I think that is what you said, right? Like, because delta larger than 1/2 is basically irrelevant perturbation. And if you tune irrelevant perturbation too large, you could destroy the irrelevance. You could make it relevant somehow. So in that case, you do have a finite threshold, but the threshold is smaller than 1.
Okay. Thank you.
Hi, maybe I turn on my video. So, hi. Maybe could you explain again what you mean by the decoding threshold? You must have said this, but I didn't quite get what you meant by that.
Yes. So sorry for skipping it. So threshold just means that like now everywhere you have probability P to have an error. And now I want to ask whether this error can be decodable or not. And so of course that depending on the P, right? If P is very small, then probably you can correct the error because the error rate is small. But like for example, for the repetition code, you can tolerate at most 1/2 of the spins get errors. So in that case, the threshold will equal to 1 by our convention. Yeah, that means that every qubit has P over half probability to have an error, and the maximal amount of P like is which you can correct is called the recording threshold.
So I come really from the error correction side of things. And for us, the threshold has a very specific meaning. And what it means is that if I increase the distance of the code, the logical error rate actually decreases. Okay, the value of P at which if you increase the distance of the code, the logical error decreases, right? I think I'm having a bit of a disconnect because I'm not recognizing where in your construction you have this notion of a distance.
Oh, yeah, we don't really have a distance. Yeah, because talking about distance in this CFT code is actually a little bit subtle. But talking about threshold is kind of natural because you can have each qubit, like for example, for the toric code, you can like say just each qubit has some probability of having an error, right? And then you use the minimum weight perfect matching protocol to correct that error. And you say that in a thermodynamic limit, the error threshold, the error cannot be greater than the random bound Ising threshold. So, so in that sense, we mean threshold. That I think what you said is also right. Like if we increase the system size larger and larger, the error rate also get to smaller and smaller. But that is also a definition of the P to be below the threshold, and that also applies here. So in this case, if you have a correctable error, that means if you fix P to be like smaller than PC, that will mean that IC, like this coherent information will increase as the system size increase.
Okay, so I should think about your system size as being something like the distance of the code, is it?
Yeah.
Okay, thank you.
So a question. Should I think, so I think maybe you mentioned this before, but should I be thinking of fixing the number of code words as finite and then sending n to infinity, where n is the thermodynamic limit?
So in this case, we don't really talk about code distance. We just take the system size to infinity.
No, I'm not talking about the code distance. I'm talking about the code rate. Like how many logical codes can you?
Oh yeah, we fix it.
You fix it. So your code rate is going to 0 then.
Yeah.
But like, how could you scale the number of logical qubits encoded in a way that also, diverges with n?
Yes.
So that
yeah. So yeah, you can choose k to be order log L. That is what we can prove. Yeah, it can increase, but not too much. You cannot have a finite code rate.
I see. Thank you.
Yeah. Okay, so I guess I'm a little bit going over time, so just let me mention that this main result is tested on the IC model, and you get something called scaling collapse of coherent information, and depending on whether whether you get a positive exponent or negative exponent in your scaling collapse, you either get a uncorrectable error or correctable error, and here, like this exponent being positive or negative just simply means that when you increase the system size, whether the coherent information become larger or smaller. So for the X error, if you increase the system size, the coherent information actually becomes smaller. But for the Y and Z, like actually the coherent information becomes larger. So that is what we numerically have confirmed. And also, as I just answered Wenwei's question, like so you can make the logical subspace actually a little bit larger than order 1, but not too much. Okay, and finally, I will just using 2 more minutes to go through the physical part of the story. So why does that ever happen? Why is X error not correctable and Y and Z they start to be correctable? And the reason lies beyond the long-range entanglement in the quantum critical state. So as we know, if you have a ground state of a critical system, if you look at the entanglement entropy between subsystem and the rest of the system, you get this log L behavior with some coefficient that is proportional to the central charge C. So central charge basically counting like how much entanglement there is. So now you have long-range entanglement in the ground state. That is good, right? Because long-range entanglement is needed for error correction. But then if you have noise inserted, that is like your system is interacting with some environment by some local decoherence, then actually the amount of entanglement could actually just change by applying noise of the to the ground state. Like for example, you can measure the amount of quantum correlations after decoherence by this logarithmic connectivity. And as we can see that, like for the pure state, the connectivity is still logarithmic in system size, meaning that there are still many quantum degree of freedom. But if you apply X dephasing, then actually you look at the red line in the figure, it actually means that like your like long range connectivity just disappears, like the connectivity is almost equal to 0, and that means that there's no much quantumness as long as you apply a little bit amount of X dephasing. And here I'm showing the example of like 0.1 strength of X dephasing. But for Y and Z, you still get this log with the connectivity. So that means that long-range quantum correlation still exists there. So that is why like the code can tolerate Y and Z dephasing. So that also gives us like a unification of like the mixed state phase and quantum error correction property. That is like a quantum error correction is only possible if and only if there is there's still long-range correlation after you're applying the noise. Sorry, long-range entanglement after you're applying the noise. So that's the physical interpretation. And there's also some boundary CFT stuff, which unfortunately I don't have time to go into, that explain all this behavior. So okay. So to summarize, so we have shown that CFT low-energy subspace form an approximate quantum error correction code, and dephasing noise has a finite error threshold if and only if like the scaling dimension is bigger than 1/2. So that's the main result of our paper. And finally, that the logical subspace could increase, but not too much with the number of physical qubits. That's the distinct feature from gapped case. And finally, we have shown that error correctability has some relation with the long-range quantum entanglement that is an activity in the resulting mixed state. So there are a few feature directions that can related to holography and constructing the decoder, and how complex the decoder could be, and finally, can there be an improved bound on the logical subspace? In fact, we don't really expect log L to be the best one. Like we could be, for example, just 1 log. So yeah, but that requires further study. Okay, so that's all.
Thank you so much.
Yeah, thank you. Thank you for the nice talk. Any questions from the audience?
Yeah, I do have a question. So it's tangential really related. So if I want to more seriously think about CFT as a code, what would be the unitary logical operator like?
Good.
If I choose to use the subspace that you explained to us.
Okay, I'm pretty sure that the logical operator is not very simple. It's of course not transversal, but it's very yeah. The logical information is the logical operator is very complicated and could be given by a mirror actually. So so if you have this W encode, the logical operator can actually be given by like you first like reversely run this encoding unitary, and then you just do a bit flip on the original logicals, and then you run the encoding back. So yeah, so that is the logical unitary, but it must be very, very complicated.
I see.
Yeah.
I see. Okay, maybe another question is, since icing in a certain sense is just free fermion, right?
Yes.
So if I don't want to talk about CFT, but instead a Fermi liquid, just generally a Fermi gas, if you wish, let me just say Fermi gas. Can I say a Fermi gas is also error correction code in this sense?
Yes, like now you have a gapless system, but yeah, as opposed to like a usual critical system, like your gapless degree freedom kind of form a manifold instead of like yeah, it's more complicated than usual like gapless system than usual critical point, right? It's like more complicated. But I'm pretty sure that if you regard like the low energy excitation that is like you move one electron in the Fermi C outside the Fermi C. Yeah, that kind of excitation can be treated as a code word. Yeah, and yeah, and there are still infinite number of them, and you can study the coding properties and how much error you can tolerate. For example, whether you can tolerate a finite threshold of of BCS coupling, of finite threshold of number operator dephasing. Yeah.
I see. Thank you.
Any other questions?
I have a question. First, thank you very much for a nice talk. So you said that X area is not correctable in your example. So I'm curious if X area is localized at some point, is this area related to the defects in CFT in some sense?
Yes. Yes. But I also tell you that X error can be corrected if it is localized. Like what cannot be corrected is that you apply X everywhere with a finite probability. So in fact, if you allow the probability to decrease with the system size, actually we can show that if you allow the probability to scale as system size to the minus 0.5. Sorry, minus 0.75. If you allow this error rate to decrease with the system size, then still the X error can be corrected. You can just not make like P as order 1. Yeah.
I see. Thank you.
Yeah.
Maybe one more question. Okay, if there's no more question,
I'll ask one actually, so if that's okay.
yeah.
So I guess my question would be more on okay, so given like a certain error model, is there like a systematic way to find this Hamiltonians with this you know, like nice gaps where you can define your codes in this low energy eigenstates?
Yeah, okay. So you want to do some kind of reverse study where you yeah. But okay, the philosophy of quantum error correction is kind of it's not exactly as that. Like it's basically want to want to tolerate as much error as possible. Like given a noise model, if your noise model only consists of, like, say, the X operator, then repetition code can just do the job. But what makes things more complicated is that your noise could be like correlated or, long range interacting or whatever, right? And in that case, things become more and more complicated. But there are some very general thing in quantum error correction, which says that, for example, the topological code can serve as an example where it can tolerate any kind of local error to a finite threshold. So that type of statement doesn't really care whether your like noise is X or Y or Z. Like any type of local error, it can tolerate to some threshold, but we don't know the threshold if you don't exactly specify the noise model to me. But yeah.
Yeah, sure. I mean, so I mean, I guess like my question is more of kind of like, okay, so if I have a certain error model, then I know, I can just check the nil Lamb condition and all that, and whether my code space can correct that error model. So I guess like the question is more on like, is there like a mapping between, like a given code space to like this Hamiltonian stuff?
Oh, okay.
Like
I
this
guess you, yeah,
properties.
I see. I guess you want to, yeah. So you, from the code subspace, you want to find the Hamiltonian.
Sure.
Okay. Yeah. So if the code is the stabilizer code, then you just sum up all the stabilizers to make the Hamiltonian, right?
Okay.
Yeah. But in other case, I think
Also, in
yeah.
general, if you know a single energy eigenstate in general, you will already obtain the entire Hamiltonian, right?
Yeah. Actually, yes. So yeah, generically speaking, the ground state seems to have enough information about the Hamiltonian, where there's always some type of tomography that gives you back to the Hamiltonian. I think for 1D, or 2D, if you have MPS or PAPS, then there's a unique local Hamiltonian. There's local Hamiltonian, where the unique ground state is the MPS or PAPS that you are given. So that is called parent Hamiltonian. So that part I think we know. But if your state is not given as a tensor network or stabilizer state or free fermion state, like if the state is more complicated, let's say like you want your state to be a superfluid or whatever, then things could be more complex.
I was referring to a previous work which says starting from a single eigenstate of a quantum many-body system, one can in principle reconstruct the local Hamiltonian such that this state is indeed an eigenstate, not necessarily the ground state of this Hamiltonian. This method has a subtlety. The outcome of this method is actually not necessarily the Hamiltonian if there's another continuous symmetry. This method is really to reconstruct all the conserved densities of the system. So it can either be the Hamiltonian, or if there's some other continuous symmetry, it can be the conserved densities corresponding to that symmetry.
I see. But so yes, okay, I see. So basically, the symmetry, the information of the symmetry can be read off from the state.
From a single eigenstate, which doesn't have to
From a
be the ground state.
I see. But what kind of symmetry? On-site symmetry, right? Just on like.
I think actually any symmetry generated by any local conserved density can be read off. It doesn't have to be an on-site symmetry. Like the Hamiltonian itself is not an on-site symmetry, right? Hamiltonian is a symmetry of the Hamiltonian, but it's not an on-site symmetry.
I see. Okay, yeah. Well, that's more. Yeah, that's very interesting. I see. Good.
Yeah, that work is by Xiaoliang Qi and Daniel Rallard.
I see. Thanks.
If you don't mind, could you type down the in the chat like this reference?
Give me 1 second. Sorry for other people who are staying. Feel free to go and just find this reference.
Mhm.
Okay, let me quickly type it down here. Yeah, it's in the chat. Wait, sorry. I think I sent it to the wrong channel. Do you see it?
Yes, awesome. Thanks very much.
Yeah,
Okay,
that's
thank you.
it. Thanks.
I guess we have pretty good discussion. Yijian, thank you for the very nice talk, and I also would like to thank everyone for participating and asking questions. The next talk will be in a week. Thank you. Bye.
Okay. Thanks, Liu Jing. Bye.